All right, guys. Sorry for a bit of a technical hiccup because of the computer not working. All right, guys. Okay. So in the meantime, we'll do things on paper while we are waiting for the technicians to come in. So we looked at a number of gates last week. We looked at a number of gates. We started off with the. So this is a recap. We started off with the NOT gate, which is an inverter. So an inverter has a single input, single output. You plug a bit in, right? You connect a bit inside, and you have and you end up with an inverted bit, right? So if you put in a 1 inside, you get a 0. Then we looked at the AND gate, right? So this is some of the stuff which we looked at last week. We looked at the AND gate, right? The AND gate is basically both bits have to be high or positive in order for you to get an output high, right? Both have to be in the affirmative. And this was a scenario where I said, okay, if you're using an air conditioning system and you want to have multiple sensors around the room, so that's where you use an AND gate, right? Okay, now then we said, okay, we want to look at an OR gate, right? An OR gate. Okay, we looked at an OR gate. And in the OR gate, as the name says, the name of the particular gate gives away the function in itself. In an OR gate, you have a particular scenario where you've got two inputs, and either one, any one of them is high, the output will be high. All right? Okay, so this is recap. Right? Let's recap on the next gate, which is a buffer. Well, the name buffer gives it away. So most of the times you will end up with gates where you have a name. The gates are named very appropriately, right? Very appropriately. Well, at least for these first 4 gates, right? Buffer is basically a gate which is holding the bit. So whatever input signal you give in, that will come out. Then you have NAND gate. Now, this is the catch. NAND gate is not AND. We've already learnt about an AND gate, and we've already learnt about a NOT gate. So what you do is you put an AND gate in series, with the NOT gate. And that little thing is called the bubble. So basically, it's, if you look at the truth table, it's the exact opposite of an AND gate, right? NAND, which is short for not AND, is the exact opposite of AND. Then the same principles apply for OR and NOR. You have NOR gate, right? Okay, you have a NOR gate, which is same as saying not OR, right? So up till now, it's very straightforward. Now the next gate which we looked at, the last one, was XOR. Okay, the last gate which we looked at was XOR, exclusive OR. This is the trickiest gate out of all of them. So when we look at basic gates, which we did last week, NOT, buffer, AND, OR, NAND, NOR, those are simple free rides, right? You can just have a look at the name, you can easily understand what's happening. With XOR, the behavior changes fundamentally. It is like an OR, except for it's going to be exclusive. So in an OR, 0 or 0, if you look at an OR gate, 0 or a 0 will give you 0, that's fine. Second line, 1 or a 0 will give you a 1. 0 or a 1 will give you a 1. In the last line, if it was an OR gate, a 1 or a 1 would give you a 1. But in XOR, a 1 or a 1 gives you 0. All right? Okay? All right. So this is the particular XOR situation. An XNOR is basically you take an XOR and you plug in a NOT gate. So therefore, you put in a bubble To minimize the circuit symbol for a NOT gate, you just put in a little bubble, and that's XNOR, which is exact opposite, which is the inversion of an XOR. All right. Now, while we're waiting for the computer guy to come in, let's start off anyway. Okay. So today's lecture, in today's lecture, we will be looking at some Boolean algebra theorems. Fundamental theorems. There are many theorems, but we will be looking at the fundamental. We'll be looking at the fundamental theorems. All right. Okay. Let's go through theorem 1. Theorem 1 is the associative law. Now, back in secondary school, when you were in year 8 or perhaps maybe in year 7 or year 8, we learned some of these rules, but these 3 rules you may recall. Associative rule, commutative, distributive. We learned this somewhere around year 8. I don't know which year did you guys learn that in. When I was in class 8, I think. So the same rules apply. The same rules apply. But this time to Boolean algebra. Remember, in Boolean algebra, we have AND, we have OR, and we have NOT. We don't have plus and multiply. When we learned it in class 8, it was with regards to addition and multiplication. Even though the symbols look very similar, but it is a different item. So let's have a look at the associative law. Okay, number 1. You have A or B or C is the same as saying A or B or C. Note over here that when I'm reading that particular Boolean algebra line out, I'm not saying A plus B or plus C, I'm saying A or B or C. So for every theorem, or in fact most of the theorems, you will have an OR version and you will have an AND version. All right? You will have OR version and the other one will be AND version. So this is for OR. Okay, let's just put that in a box to indicate that that's the OR version. All right. Now, whenever you write out Boolean algebra, it's very simple and straightforward for you to read that simple mathematics. But as an engineer, even the mathematicians, even the guys who did MA 161, they would visualize this particular Boolean algebra expression as just a straightforward rearrangement and application of a fundamental principle which we've learned in primary school in class 8, right? Year 8. Associative law, you just transfer your knowledge from primary school to here and you say, okay, this is this. But this is where the leap comes in terms of our engineering knowledge. Now, look at this. I had this all on our document thing, but just wait. So that would equate to okay, so that's the left-hand side. That's what I've drawn on the left-hand side. And this would be the same as okay? That would be the same as that there. Okay? So this is where the leap comes in. When we are applying any theorem, right? We are doing the first theorem in this particular course, which is the associative theorem. When we are applying any theorem, right? And it so happens this theorem is a repetition of one of our mathematical theorems which we use for addition and multiplication. The reality is that on the hardware level, you are flipping circuits, or you are rewiring, rearranging, reducing circuits. All right? So if you look on the left-hand side, you have, if if you look on the left-hand side, you have a circuit with two OR gates, and look at how A, B, and C is wired up. And on the right-hand side, you have again two OR gates. This time, it's wired up in a different manner. So the important part to realize is, when you are rewriting or reducing Boolean algebra, right, you are actually changing something at the hardware, right? And eventually, our objective is to reduce the number of gates or to simplify the gates as much as possible. All right, let's look at, so the question may arise is, how do you prove this? How do you prove something like that? Well, for every theorem, some of the more advanced theorems, you rely on earlier theorems. But something as fundamental as this, you would, one of the easiest ways to prove it without getting into fundamentals of mathematics is to draw a truth table. To draw a truth table. So what you do is you'd have A, B, C, right? Okay, and then you would maybe have the output for the left-hand side, and then you have the output for the right-hand side. Okay? So in your free time, because I don't want to go into doing each and every line over here, in your free time, I expect you to, during your study time, I expect you to populate this particular table and see if the left-hand side, which was A or B or C, or A or B in brackets or C. I expect you to populate this table and check if that is correct. Let's move on to the next theorem. All right. It's not the next theorem. It's actually the same theorem, but the end version. But the end version. All right. So you have, in terms of Boolean algebra, look at the little dot. We don't call it dot. We don't call it multiply. We call it AND. A and in brackets, B and C will be the same as A and B in brackets, and then and C. All right. So once again, we will have, because we are saying that these two are equivalent, and we are using the associative law. Because we are saying that these two are equivalent, we are actually saying, what we are actually saying is that this particular circuit is the same as that. So the circuit on the left-hand side is the same as the circuit on the right-hand side. So once again, my point is that when you are looking at Boolean theorems, there is always a rewiring or reduction or simplification of the circuitry. Right? In this case, there's not much simplification, but as we move on to other theorems, you will start to see that things become very handy, some of these theorems. Let's look at the next theorem. Okay, Theorem 2. By the way, guys, there is the slides, just because our computer is down, the slide for this is up on Moodle Shell, okay, with all the diagrams. So, okay, the next theorem is commutative. The next theorem is the commutative theorem. Once again, that's something which we remember from primary school. So commutative was, in terms of primary school, if it was something along the lines of x plus y is the same as saying y plus x, yeah, right? Or x times y is the same as y times x, right? So over here, you have A or B is the same as saying B or A. Once again, every theorem, they will have an AND version and you will have an OR version, right? So you have so basically what we're saying over here is that what this theorem means in hardware, what it actually means in hardware is that all we are doing, we're using a big word like the word commutative, so many alphabets in that word, right? But in reality, in hardware, that's what matters in the end. The circuit matters. We're not doing Boolean algebra for the sake of just writing on paper. It's got to reflect something in hardware. What it means is flipping the inputs in hardware. Right? In terms of mathematics, it was x plus y, x times y is same as saying y times x. But in terms of digital logic design, it means you take a gate, you flip the inputs, it gives the same answer. It gives the same output. All right? Okay? Let's look at the other version. What version are we on next? Okay? And as part of your homework, guys, I expect you to prove this using the truth table. Prove using the truth table. So for every theorem, maybe do a new theorem on a new page, even though there's some space left at the bottom. That's fine. All right. But you've got to fill that up in your free time to prove it. Right? Okay. Let's have a look at theorem number 2, part 2. Theorem number 2, part 2. You have A and B is the same as saying B and A, right? So if you have a gate, okay, this is the AND version. This is the AND version, okay? And you have A, B, B, A. Once again, all you're doing is you are flipping the gates. And how do you prove something fundamental like that? Well, I expect you to do it using a truth table. Let's move on to the next theorem. Right, so I'm not going to leave some space, but I expect you to do it. The next theorem is Theorem 3, which is the distributive theorem. So these three are fundamental. If you recall, these three are fundamental, and we know this from our days in school. Okay, have a look at this. This is where things become tricky. Okay, as far as this one goes, that's straightforward, right? Is the same as saying A or B, A and B, or A and C. Let's have a look at this. Makes sense even from your earlier mathematical knowledge. You would say, hey, we are doing mathematical expansion. We are doing mathematical expansion. All right? Okay, maybe it does look similar, because you know, the signage and all that is similar, but you'll see this in the next round. All right? Okay. Let's have a look at the circuitry. So what we started off with was you have A, that's B or C. B or C. And then that's AND. And what we are trying to say over here is, let's have a look at this. Look at this way of drawing. Okay, because you are now being introduced to, up till now you were only looking at individual gates. Now we move to the next level, we are drawing circuitry. Look at how I draw this circuitry. So generally people would do two sets of inputs, but this is the way you can draw it, which makes it neater. So you have two AND gates which feed into right, and because you've got A in common, this junction you just put a little dot over there just to indicate that it is in common. And you can do a B over there, you can do a C over there. So have a look at that. Okay? Left hand side, right hand side. So in this case, actually what happened was, we have actually gone from 2 gates on the left hand side and we have increased the number of gates, right? So sometimes some Boolean theorems in certain directions will increase the number of gates. But if you were to say start off from the right hand side, we would have easily been able to reduce the number of gates. So let's put it in a practical manner. If each gate costs 20 cents, right, you would have saved how many? How much would you have saved when you applied distributive property? You would have saved 20 cents or maybe 33% savings. Yeah, you would have saved 1/3 or 50% savings, right? From 60 cents you go down to 40 cents. All right? Okay. Let's have a look at how you prove this. So I want you to prove this. So I'm going to draw the table headers which you would need to fill. Prove using a truth table. So you have A, B, C, AB, right? AB, AC, BOC, another double line. You have AOB, A and BOC, another double line, AB or AC. There you go. So you've got to populate this particular table. This is the manner in which we prove, this particular table. So in the end, these two columns, the left hand side and the right hand side, they've got to be equal. They've got to have identical columns in the end. All right? Okay. Okay, let's move to another one. Now, let's move to something trickier. So up till now, it's all smooth riding. We are again, remember, for most of the theorems which we've done so far, for theorem 1, we've had an OR version and an AND version. Theorem 2, OR version, AND version. Theorem 3, distributive. We've got the first one. Let's show you another one. This is where you start to see. Remember when I said that when we look at this theorem, you would say, hey, that's just straightforward expansion. All he's done is just expanded it and it's calling it a theorem. Now you will see the theorem become different. So for those of you who were thinking of AND as multiply and OR as addition, this is where you get proven wrong. A, OR, B and C is the same as A or B and A or C. Have a look at that. I want you to spend a few minutes paying close attention to this. This is where, for those of you who had insisted at the back of your mind that this plus symbol is OR and it behaves exactly like addition, and this dot symbol is an AND and behaves exactly like multiplication, this is where things fall apart. It is not addition, it is not multiplication. It is and it is or. Boolean algebra is different from fundamental mathematics, right? Fundamental, or maybe the word is rudimentary mathematics. What you did with addition and multiplication is totally different. Do not confuse the two. So have a look at this. If this was your guys' thing, if we were to apply a normal addition and multiplication, this would have been A and C, A and B, A and B and A, right? So we would have ended up as 4 terms. But over here, if you look at it, all we've got is A or B and C. Yeah? Right? So this is where it becomes different. Right? So this is how, up till now, everything seemed like just a replica of rudimentary mathematics. When I say rudimentary, I mean things which you learned in primary school, right? Or earlier junior high school, right? But now it doesn't make sense because this is, again, I repeat, this is Boolean algebra. That symbol there is or. This is and. Totally different ball game. Totally different ball game. Right, so let's have a look at this. B and C There we go. Oh, sorry, not yet finished. There we go. Okay. Now, how do you prove this? How do you prove this? Again, for these first 3 theorems, or first 6 theorems, I think, you can only prove it using truth table. So let's go and attempt this truth table. Let's attempt this truth table. So you have A, B, C, you have B and C, you have A or B, and from there you have A or C. Then over here you now put your left hand side, which is A or B and C. And over here you have A or B, A or C. All right, let's now go ahead and attempt this. So, guys, let's have a look at this. There are three inputs. There are 3 inputs on the left hand side, right? 3 inputs we started off with. So how many possible combinations will there be? 8 combinations, going from 0 to 7. So you have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. There we go. All right, now let's fill this up. B and C. Can you help me here now? Let's do this problem. B and C will be B and C. B is 0, C is 0. B and C will be a 0. B and C. B is 0, C is 1. There will be 0 because one of them is 0. This will be a 0. 1 and 1, 1. 0 and 0, 0. 0 and 1, 0. 0 and 1 and 0, 0. 1 and 1, 1. Right, let's look at A or B. Let's look at this. Let's fill up this column. A or B. All right. So A or B, we're just looking at the first two columns. 0 or 0, 0. 0 or 0, 0. 0 or 1, 1. 0 or 1, 1. 1 or 0, 1. 1 or 0, 1. 1 or 1, 1. 1 or 1, 1. Let's look at A or C. 0 or 0, 0. 0 or 1, 1. 0 or 0, 0. 0 or 1, 1. 1 or 0, 1. 1 or 1, 1. 1 or 0, 1. 1 or 1, 1. Now, let us look at this last one. Let's look at left-hand side. A or B and C. So we can pick up A from this first column. We can pick up A from this first column. And B and C, we can pick it up from here. So what do we get? 0? Yeah? 0 or 0 will be 0. 0 or 0 will be 0. 0 or, where is it? 1 will be a 1. 1 or 0 will be a 1. 1 or 0 will be a 1. 1 or 0 will be a 1. 1 or 1 will be a 1. Let's now look at this last right-hand side, which is basically we pick up from these two columns, right? So you have the original inputs on the far left. Do you see that double line? You have some intermediary calculations, some working inputs, right, which second or intermediate inputs. Then on the last line, we have the output. So this is one output. Let's look at the other output. So 0 or 0 will be 0. 0 or 1 will be 1. 1 or 0 will be, oh sorry, it's an end, eh? 0 or 0, 0 and 0 will be a 0. 0 and 1 will be a 0. 1 and 0 will be a 0. 1 and 1 will be 1. 1 and 1 will be a 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 1. All right, now tell me, the key question here is, does that column equal? Yes, those two columns are equal. Those two columns are equal. So using our truth table, we have just proven that very unusual Boolean algebra theorem, right? Where your normal rudimentary mathematics didn't make any sense, but it's working in Boolean algebra. That's why this is called Boolean algebra. Okay? All right. Now, let's now have a look at the fourth theorem. Which is identity and null element. Identity and null element. All right, now, what does the word identity mean? Okay, so let's go switch back. So a lot of the times we have to flip back to our knowledge of rudimentary mathematics. So identity, tell me, in terms of multiplication, anything multiplied by 1 is equal to itself, right? So x times 1 or y times 1 or z times 1 will always equals to x, y, and z, right? So 1 in terms of multiplication is what? Is the identity, right? Is the identity. Now, all right, that's straightforward. Now let's have a look at addition. Tell me, in terms of addition, what do you add with, what number do you add with to get the same input? Input, yeah. Sorry, somebody said it. 0, yeah. So anything added to a 0 in terms of addition, anything added to a 0 will give you the same output. So 0 in terms of addition is an identity. And for multiplication, the identity is 1. Okay? So let's now look at another concept. Another concept is the null element. The null element. The null element, tell me, this only exists in multiplication, right? In rudimentary multiplication. What times a number will always give you a fixed answer? Yeah, right? So in terms of multiplication in your primary school mathematics, anything times a 0 will always give you a 0, whether it's a million times 0 or whether it's 2 times 0. You'll always get 0. So 0 in terms of multiplication in your primary school mathematics, rudimentary mathematics, is a null element for multiplication. But for addition, there is no null element. But over here, we will have, right? So let's have a look. So let's start off with the OR gate. Let's now split this up. I'm going to split this page up. Okay. Now, we say A or 0 is what? What is A or 0? Let's have a look. Let's have a look. Right? So let's put an OR gate. How do we actually see this? And you have your input A, and your other input is tied to ground. Do you see that? Your second input is tied to ground, and you have, let's say, you assume the moment you have your second input tied to ground, the assumption there is that that is logic 0, right? That is logic 0. Okay? Now, what is the output? What is the expected output over here? Well, let's now look at the truth table. Eh? Let's draw a truth table. So you have your input A. You have your input A. You have your input B. And you have your output X. Right? Okay. Input A is open. Input B, what have we done with input B, guys? We have fixed it to 0. Now, for input A, there's only one input which we're talking about. So how many possible combinations? There's two possible combinations, 0 and 1. So 0 or 0 gives you a 0, yeah? 1 or 0 gives you a 1. Is that correct? So in the end, what can we say? When the input was 0, the output was 0. When the input was 1, the output was 1. So A or 0 gives us A. So therefore, what can we say? We can say that 0 is the identity for the OR gate. 0 is the identity for the OR gate. All right? Okay. Now let's look at the next one. what if we had 1 OR with an input, okay, in the OR gate? So let's have a look at the circuitry. The circuitry would be as follows. And our input over here is A. So because that's a plus 5 volts, this here is assumed to be logic 1. What would be the output? Think of your OR gate truth table. 0 or 0 gives you 0. 0 or 1 gives you a 1. 1 or 0 gives you a 1. 1 or 1 gives you a 1. Every time there is a 1 present, think of the truth table. You can look at, you can refer to it from last week Thursday's notes. Every time there is a 1 present in the truth table, what is the output? 1. Output will always be 1. Right? Can you see the identity? The output is fixed now. Whatever we put in into A, the output is now fixed. So when it comes to an OR gate, your 1, okay, so the null element for the OR gate is 1. The null element for the OR gate is 1. All right. Let's have a look at the next one. Let's look at A and 1. Oh, guys, I did not fill this out over here. A or 1 is equal to 1. A or 1 will always equal to 1, and A or 0 will always equal to itself. So that's anything which equals any operation which brings any element which brings the operation to answer and bring the input to equal to output is known as identity. So multiplication, you remember that we discussed. But over here, OR gate, the identity is 0. For OR gate, 1 becomes the null element because the output becomes fixed, right? But early on, if you want to think of this like a plus or addition, there is no such thing as a null element for addition in rudimentary mathematics, okay? But in Boolean algebra, in Boolean mathematics, yes, 1 is a null element. Okay, now let's have a look at this one. So you have plus 5 volts, which is the same as saying logic 1, and you have A. And you are saying, what is the output? What is the output? Well, let's have a look. Let's have a look at the truth table for AND gate. Zero, zero. Zero and 0 is giving you 0. 0 and 1, 0. 1 and 0, 0. 1 and 1, 1. All right, now have a look at this, guys. When you have a 1, so A, let's leave A as is. Whenever you have a 1 in the table on the B side, what is the output? The output is the same as A. Yeah? Whenever you have a 1. So that is A. So what can you say over here? What can we say over here? Well, we say that 1, logic 1 is the identity for the AND gate. Okay. AN. Okay, this table is only, what I've done is I've drawn the truth table of the AND gate. Yeah, just a simple truth table of the AND gate from last week Thursday. Right, 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1. Right, this is just the truth table. Then I said, okay, A is over here, and B, we only look for the cases where B is equal to 1. So we are isolating the places where the second input is 1. So 0 and 1 gives you 0, 1 and 1 gives you a 1. And X is the output, what we're saying from a normal truth table point of view. Okay. In that case, X is equal to A. Yeah, X is equal to A. If you only take those two lines, of course. All right. Okay. Now, let's look at the next one. A and 0. A and 0. So in order to do a 0, you've got to connect it to ground. Right? Let's now look at this side over here now. Again, let's now refer A, we leave A as is. Let's now isolate the times when, the second input is equal to 0. So this was a logic 0 here. The times when the second input was equal to 0, it's this place here and that place there. Two cases.